Hi everyone, and thanks for coming. My name is Jake Hesselink, and I'll be presenting my project entitled Identifying Auditory Artifacts in Small Rodent Focused Ultrasound Neuromodulation. So focused ultrasound neuromodulation is a non-invasive technique that uses focused ultrasound waves to modulate the activity of brain tissue and can even target deep brain areas. The mechanism by which it stimulates brain activity is somewhat unclear. Many studies will record motor responses to ultrasound, while one somewhat recent study found indirect auditory activity during ultrasound delivery. We want to identify the source of this auditory activity so that we can help refine the technique and lead to more reliable results in the future. We hypothesize that the delivery of ultrasound leads to vibrations in the skull within the audible range of the animal, and these vibrations can therefore contribute to the cortical and motor activity seen in these studies. So we hypothesize that motor responses and skull vibrations will be recorded from both motor and non-motor target stimulation. Our objectives in this study were to record motor responses from these two targets and compare them, as well as detect sonic level skull vibrations and mitigate these vibrations by randomizing our pulse repetition frequency, or PRF. Our methods: we had a main study that used 12 animals. We delivered ultrasound to a motor and visual cortical target using the RK50, which is a benchtop stereotactic guided focused ultrasound delivery system. We used 477 kilohertz ultrasound with a 1.5 kilohertz pulse repetition frequency and a 4.2 watts per centimeter squared spatial peak temporal average intensity. We recorded responses to this ultrasound using a video camera and electromyography electrodes, and we also recorded vibrations at the level of the skull using a contact microphone. During our ultrasound treatments, we reduced our isoflurane anesthesia from 2 to 1%. We then did a small study which used either a fixed or random pulse repetition frequency. During this study, we also delivered auditory stimuli using a speaker to match the frequencies seen in our microphone signal to see if they affected motor activity, which we deemed that they did not. Looking at our motor results, you can see here a representative video where the ultrasound goes on and the tail will flex. You can also see a representative EMG trace here showing the same thing. And looking at our motor response rates, there was no significant difference between our motor and visual targets. In fact, there's very low motor response rates overall and slightly higher responses in the non-motor target. Moving on to our auditory results, we did record an auditory artifact at the level of the skull. In our audio signal that we recorded, we saw a 1.5 kilohertz peak frequency, which seems to correspond to our PRF. The presence of this auditory artifact did not seem to have an effect on motor response rates. However, it is possible that an artifact would be present at the skull without our microphone detecting it. Randomizing our PRF did seem to mitigate the frequency peaks seen in our microphone signal. However, the effect of this on motor responses is still unclear. Discussing these results, the auditory artifact seems to be mitigated by altering the delivery envelope. For us, that meant randomizing our PRF, but in recent literature, it's been seen that smoothing the ultrasound delivery envelope can mitigate the auditory responses seen in the brain. It's also important that motor responses do not seem to be dependent on this auditory artifact. Motor responses do seem to require a very low level of anesthesia. In fact, in comparing our results to the literature, it seems that you need a nearly 0% anesthesia level to record reliable responses. These motor responses can also occur from non-motor target treatment. The mechanism of ultrasound is somewhat agreed upon in the sense that the pressure wave of ultrasound increases the excitability of neuronal membranes. However, this could easily affect different neuronal subtypes preferentially, as well as different brain processes such as arousal. Based on these statements and other evidence in the literature, I believe that it's highly likely that ultrasound delivery affects network activity in the brain and can therefore lead to somewhat inconsistent patterns of activity. The limitations of our study is that our microphones lack durability, and we could not reach the low anesthesia level needed for reliable responses due to the stereotactic setup that we used. In the future, we hope to refine our technique by finding more appropriate ultrasound parameters, adjusting our setup to allow for lower anesthesia, using additional measurement methods as well as complementary imaging techniques, and using in vitro study to look at the effects on different neuronal subtypes. I'd like to thank the University of Calgary as well as my funding sources and my lab mates. If you'd like more detail on my project, you can go to my poster PDF, and if you'd like any questions, feel free to ask them.